Hi all, have a good day. I'm K. Surya, working as Assistant Professor in the Department of ECE at SNS College of Technology. So in this video, let us see about applications of network theorems in electronic and electric circuits. So this is first we need to know why we need to go for network theorems. So the empathy part here is to simplify complex networks into simple networks. We need some methodology. Okay, so we are going to define a methodology to simplify complex circuits into simple circuits. So for that, the method used here is the network theorems. So the network theorems are used in various applications. So we will be seeing the applications of network theorems. So it is developed in such a way that it could analyze a circuit with any type of complexity. So different types of networks theorems are superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, reciprocity theorem, and so on. So first we will see about the applications of superposition theorem. So you know that it if a network comprises of more than one source, the resulting current and voltage in the network can be determined by taking each source independently and superposing the results. So this means that the electromotive force present in the circuit is equal to the total sum of the voltage drop across any form of the circuit component. So this theorem does not apply to nonlinear circuits. So the requisite of linearity indicates that the superposition theorem is only applicable to determine voltage and current but not power. So power dissipation is a non-linear function which does not algebraically add to an accurate total when only one source is considered at a time. So the application of superposition theorem requires two or more sources in the circuit. Next one is Thevenin's theorem. So it basically gives an equivalent voltage source corresponding to an active network. So you know that a linear active bilateral network is considered across one of its ports, then it can be replaced by an equivalent voltage source and an equivalent series resistance as shown in the figure here. So Thevenin's theorem is used in the analysis of power systems and also it is used in source modeling and resistance measurements using the Wheatstone bridge. Next one is Norton's theorem. So it's a dual of Thevenin's theorem and it states that any linear active bilateral network considered across one of its ports can be replaced by an equivalent current source and an equivalent shunt admittance, or you can say current source in parallel with a resistor. Since the two sides are identical, they must be true for all conditions. Thus, if we compare the current through the port in each case under short circuit conditions and measure the input admittance of the network with the sources removed, voltage sources short circuited and current sources open circuited, then you will be getting In is equal to Isc and Yn is equal to Yn. So this is an equivalent circuit for Norton's theorem. So in the replacement of a large part of the network to a simple circuit, it's used in simplification of network in terms of current instead of voltage, and it accomplishes maximum transfer of power. Next one is reciprocity theorem. So it tells that the linear passive bilateral network, an excitation and the corresponding response may be interchanged. The two-port network, if an excitation E of t at port 1 produces a certain response R of t at port 2, then if the same excitation is applied instead to port 2, then the same response R of t would occur at the other port 1. So when we interchange the input and output ports, we will be getting the same result. So in acoustics and optics, the reciprocity theorem aids in understanding wave propagation, while in heat transfer, it helps in devising effective insulation or cooling strategies. This wide usability underpins the reciprocity theorem's crucial role in various scientific and engineering practices. Next one is maximum power transfer theorem. So you'll be getting maximum power delivered to the load if your load resistance is equal to the source resistance. Or load impedance is equal to the source impedance. So maximum power transfer theorem can also be implemented to linear networks. The network system along with RLC and restrained linear sources as elements. Maximum power transfer theorem functions only when there is a variable load. If not, choose the least available internal sources of impedance which paves in maximum current through the fixed load. Consequently, maximum power is expelled by the load circuit. Large sound systems are built around this process. Maximum power transfer is generated in the circuit by making the speaker's load resistance equivalent to the resistance of the amplifier. Once the speaker and the amplifier have equal resistance, both are considered harmonized. Another application is on the relationship between the starter motor and the battery of a car engine. Power applied to the starter will rely on the effectual resistance of the motor and battery resistance. When their values are equal, the highest power will be transmitted to kickstart the engine. Thank you for watching this video.